Hello, our team consisted of me, Taras Slavitsky, Oleg Husulyak, and Alexander Stadnik. Would like to present our semester project for the linear algebra course, which is real-time video decomposition. So if you're talking about video decomposition and background decomposition especially, this is a pretty frequent, pretty important problem for computer vision. And for our project specifically, we wanted to focus on the real-time part of that, meaning some certain methods would be needed to use for it to run faster. And actually, a lot of linear algebra concepts can help with accelerating the algorithm, making it run for 30 or 60 frames per second.
And I'm going to tell you how exactly our app works. So first, as you launch the application, you should move out of the way of your camera for a couple of seconds to let our application capture the background. So those couple of seconds of video are decomposed into frames, each turned into grayscale, so black and white, to greatly reduce computations furtherly because colors don't really matter in our task. Then those frames are blended into a single vector and stacked into one matrix X. Then we perform data centering, so just deducting from each frame the mean of all of those frames. And then we perform SVD on all of those 100 starting frames to get matrix U. And then we crop that matrix U to 3 top columns. And this would form our background basis, which we would use for our further computations.
Okay, now I will explain how, what happens for each new frame after our initialization. Suppose a new frame is converted to a vector called x, xt, because at time t. We then center it using our current mean, and then we project it onto the subspace. Then we can get our background estimate. And the residual. This residual is what contains the foreground motion. If a pixel is strongly compared to the background estimate, that pixel has a large residual value. Then we can turn this residual into a mask and with some thresholds that we got empirical way to get our foreground, which we will then display. But we also consider the background is a little bit not static, and that's why we use some update rule. So for this, we use QR decomposition, and this is very important things because our system does not compute full SVD for every frame because that would be too expensive. Instead, we just try to keep the basis orthonormal with QR. So we start our update from updating the mean, and it's updated only on background pixels, and also it's updated very slow because it's updated with some learning rate which we set as 0.001. So the model adapts to gradual scene changes but does not learn moving objects too quickly. Then the basis is temporarily expanded, and this means that we add the new direction to the current basis candidate, but this new matrix is not guaranteed to have orthonormal columns, and that's why we apply QR decomposition. Then the updated basis is taken as the first 3 orthonormal columns of Q. So in other words, QR does not replace the initial SVD, it just only keeps the subspace basis valid during the incremental update. It always keeps it as a rank of 3.
So now we're going to show you some demo videos, and while they are running, I'm going to tell you about some certain parameters of which determine how our app performs. So there are 4 of them. First 2 are width and height rescaling. So this is just how to which resolution our app transforms the initial video. So higher resolution means more computation means slower, and lower resolution just different. So and also we have threshold, which Oleg already told about. Basically, if it is too low, our algorithm is really sensitive, and even some tiny noise on the background will get put into the foreground. But if it's too high, only like very obvious motion in the camera will trigger the foreground display. So we put it at 20 as like a middle ground. And also we have a rank parameter which controls how many vectors we store from our initial U matrix, which we get from SVD. So if the rank is 1, we only get 1 vector, and our background model is really simple. And even any small camera like jitter or lighting flickers are gonna trigger the change in our frame, and it's going to be displayed on the foreground. But if it's too high, the background model gets too complex, the computations get really slow, and it can even start absorbing slow-moving objects, which is really bad. So we put it at 3.
So that's it. Thank you.
Thank you for your attention.